Hello, people of pre-calculus. I am going to do the notes for 3.5, continuity and behavior. Most of this is stuff that you did have in Algebra 2. If we get through this and you're still finding things kind of confusing, pages 169 to 170 in the textbook are a graphing calculator exploration, and that can be pretty helpful. All right, continuity. We say a function is continuous at a certain value, c, if it exists at that value. So if you can plug in c and get out a value, if the function approaches the same y value from the left and the right of c, and if the value being approached from both sides is the same as the value you get if you plug in c. Things that, I know it seems redundant, but these three rules describe different things, and they're broken in different kinds of functions. So if you plug in c and you can't get a value out, if f of c doesn't exist, like you're taking the square root of a negative in the real numbers, or dividing by 0, you may have an infinite discontinuity, like the graph of 1 over x squared at x equals 0. Right here, it goes to positive infinity on both sides, but is not defined right here, so that's an infinite discontinuity. It could be a point discontinuity. X squared minus 1 over x plus 1, the discontinuity will not show up when you graph it, but in fact, if you plug in -1, you're dividing by 0, so it's not defined right here. And it'll show up on the table as an error. If it doesn't approach the same value from the left and the right, you may have a jump discontinuity. Remember the greatest integer function, whenever you get to the next integer, is going to jump to the next value. That's discontinuous at x equals 1, and at x equals 2, and at x equals 3, at every integer. Or you can have an infinite discontinuity. This approaches negative infinity from the left and positive infinity from the right. If the value it approaches is not the same as f of c, it is a point discontinuity. For example, this is a point discontinuity, right? Theoretically, you could define one where it did exist at that point, and from the left and the right, it approached the same value, but the values it approached were not that point. So that would also be a point discontinuity. Some functions cannot be graphed at all. They're called everywhere discontinuous. 1 if x is rational, -1 if x is irrational. For example, 3.1, that's rational. That's a rational number. It's 31/10, right? Pi, we say it's 3.14, but it isn't really. It's a non-terminating decimal. This is not rational. 3.2 is rational. So it's not even just that it goes back and forth between rational and irrational so quickly. It's not possible to tell what the next number is. I mean, it's just not possible to graph this. It's everywhere discontinuous. If a function has no discontinuities anywhere, it is continuous. So this, any linear function, that is a number times x to the first power, you can add, you can subtract, this is continuous everywhere. X squared is continuous everywhere, x cubed, x to the fourth, x to the fifth, those are all continuous everywhere. So check if it's continuous at the given x value. To check this, you would check first whether plugging in 1 for x gave you a value, and it does, it's -3. So it passes part A. Then you want to check that the function approaches the same value from the left and the right. So what you can do, 3x squared plus x minus 7. Normally your table values are going to go, your x values will go up by 1 every time. To check these sorts of things, you really want to see much closer. So here, I want to be really close to +1. So I can go to table set this to 0.9, set this to 0.01. So it's going up by 1/100th every time, and then look at the table. All right, from the left, that is from the numbers less than 1. It's going -3.3, -3.2, -3.2, -3.1, -3.07, -3. All right, so from the left, it's approaching -3, And from the right, that is from numbers greater than positive 1, negative 2.7, negative 2.7, negative 2.8, negative 2.9, also approaching negative 3. So it is approaching negative 3 from the left and from the right, and the values it's approaching from the left and to the right, from the right are the same as the value we got out in part 1, or in part A. So yes, this is continuous at that point. Functions can be discontinuous at one point and continuous at others. That one's not. All right, let's check part A. Here we've got x squared minus 4 over x plus 2. So negative 2 squared plus 4 over negative 2 plus 2. Does this function exist for x equals negative 2? That's 0, that's 0. You can't do this. You cannot divide by 0. You can't even divide 0 by 0. So this is not defined. So this is discontinuous at this point. It's continuous at all other points, but it is discontinuous for x equals negative 2. This one, you can do this a couple different ways, and I'm going to, which you can put in the calculator. You can put in the first function, x squared, use a division for if, put your condition in parentheses, x is, and then second math gets you to the test menu, if x is greater than or equal to negative 2. And then our second function is 1 over x squared minus 4 if x is math less than negative 2. So that's how you would graph them. Part A, if you plug in negative 2, okay, remember there are two cases, so you've got to figure out which one applies. It's not less than negative 2, it is equal to negative 2, so we'll use this first case. Negative 2 squared is 4, so yes, it passes that test. Now, we're going to see what approaches from the left and from the right, and that's why doing it this way is useful, because for the area where this is defined, it'll have values, and where it's not defined, it'll say error, so you won't accidentally mix them up. Okay, we are looking around the area of negative 2, so let's say starting at negative 5. Okay, from the values below negative 2, 0.02, 0.03, 0.04, 0.08, 0.2. It's getting bigger. I'm not quite sure what it's approaching though. And here, 941, I'm not really sure. Let's get closer. So I'm going to start at negative 2.1 and go up by 1/100th each time. So, 2.4, 2.7, 3, 3.5, 4.1, 4.9, 6, 8, 12, 24, that's getting really big. It's not approaching anything. In fact, it'll get really, really large. This function approaches positive infinity from the left. From the right, that is from values greater than 2. Oh, from the right, it's perfectly normal. 3.7, 3.8, 3.8, 3.8, 3.9, 3.9, 4. That's definitely approaching 4 from the left. But from the right, it's approaching it's positive infinity. So it does not approach the same thing from the right and from the left. Fails the test. End behavior. You've seen this in Algebra 2. All you're looking for end behavior is what happens as your graph goes farther to the left, so as x goes towards negative infinity, and as it goes farther to the right, as x goes towards positive infinity. This is the one time where we want to look from the center outwards. In other things that we do, we'll look from left to right, but here we're going to look center out. So, describe the end behavior of this function as x approaches negative infinity. Well, you should graph this. I'm not going to graph each one as we go, but you should graph this and check that I'm right. As x approaches negative infinity, y is going up. It's going like this, I think. I don't know what happens in the middle, but all we care about for this particular problem, is the end behavior. So as x is getting smaller to the left, y is getting bigger, so y approaches positive infinity. As x is going towards the right, towards positive infinity, y is going down, so y is approaching negative infinity. They don't always approach infinity or negative infinity. Sometimes they approach a number, sometimes they don't approach anything at all. This one, if you graph it, 1 over x is going to look like this. It's discontinuous in the middle, but that's not what we care about right now. We care about what's happening as your numbers get very, very small, like the negative millions and the negative billions, negative trillions, and very, very big, billions, trillions. So 1 over negative 1 billion is very, very close to 0, and 1 over negative 1 trillion is even closer to 0. It's not going to get there, but it's going to get closer and closer. So as x approaches negative infinity, y approaches 0. And as x approaches positive infinity, y also approaches 0. On both ends, it's getting closer and closer to the x-axis. Last part, increasing or decreasing on an interval. A function is said to be monotonic if the function is increasing throughout the interval or decreasing throughout the interval. This graph is monotonic on the interval negative infinity to 3 and on the interval 3 to positive infinity. It's not monotonic throughout the whole graph, it's monotonic for values less than 3, and then from 3 onward it's monotonic because it changes direction. That is, it increases for x is less than 3, and then it decreases when x is greater than 3. Your only possibilities really are, let's say, increase, could be constant, that is to say, horizontal, and decrease. These are really the only things it can do. And for this, we look left to right on the graph. Increasing or decreasing describe what happens to the y value, so the interval should only talk about the x value. Determine intervals of increase and decrease. All right, I would like you to pause your video now. I'm going to give the answers. I want you to pause it, try and work these out, and then restart it to check your answers. The answers, pause it right now. The answers should be increasing for values less than 5, decreasing for values greater than 5. G of x is increasing for values less than negative 3, decreasing for values greater than negative 3. H of x is increasing for x is less than negative 2, decreasing from negative 2 to 1, and then increasing again for values greater than 1. This has 3 different intervals. Okay, so these are actually the guided practice problems. I'm going to give you the answers. Got to work them out yourself so that you can make sure you understand it. This fails the very first test. It does not exist at x equals negative 3. This one passes the first test, but it fails the second test. This function approaches from the left, that is for values less than negative 2, it approaches 6. For values from the right, that is values greater than or equal to negative 2, it approaches negative 6. So those are not the same. So this is not continuous at x equals negative 2. Describe the end behavior of each function. As x approaches negative infinity, y approaches negative infinity. As x approaches positive infinity, y approaches positive infinity. So it goes like this. And for the purposes of end behavior, we're not interested in what happens in the middle, only at the ends. This one, as x approaches negative infinity, y approaches negative infinity. As x approaches positive infinity, y also approaches negative infinity. This is going down at both ends. Intervals of increase and decrease. This is decreasing for x is less than negative 3, increasing for x is greater than negative 3. This one is decreasing for values less than -1, it's going down, increasing for values between -1 and 1, up, and then decreasing again for values greater than 1, down again. That's it. That should help you with your homework, and please remember you've got to get the notes filled out and bring them in. That's your homework grade. So don't leave them behind or just watch and not fill out. Go back and get them filled out. Bye.